In this video, we're going to take a look at the Poisson distribution. So, in a lot of ways, the Poisson distribution is similar to the binomial distribution. So, usually with both of these distributions, you almost always are working with some sort of discrete data. They have fixed rates of success. The big difference involves that issue though, because in a Poisson distribution, you're dealing with really rare events. So they have like a fixed rate of success, like a probability of a success. It's just in a Poisson distribution, that probability is extremely low. So we talk about them as being rare events, or we use the Poisson distribution to model rare events. Okay, so let's look at an example of this. So we'll use butterflies again, so you can think about how you can kind of compare this to what we did in the previous video. Okay, so here's some information. Again, we're going to start out with a parameter. So on any given day, about 22 Gulf fritillaries visit a certain flower. Okay, so that's like an average count that's been generated using years and years of data. How unusual would a count of 15 be? So right off the bat, I want you to notice that we're dealing with counts and we have no pi value right away, like no probability of a success. Okay, instead we have like average counts. This is a good way to recognize a Poisson problem or a Poisson distribution problem. I mean, what if you were going to try and figure out what is the probability of a butterfly coming in? Well, we did that with the monarchs by finding out, and the other problems, the binomial problems, by finding out how common the butterfly was in the population, and we were looking at sort of how often a butterfly, like a monarch, comes to a flower relative to all the butterflies that come to the flower. So there, we were dividing sort of, to get a probability of success, we were dividing the number of monarchs in the population by the numbers of all the monarchs in the population. And that's how we got 30%. But what would happen here? So here, if we wanted to know, well, okay, we have like these Gulf fritillaries come into a flower, but what we need is we need the number of like the butterflies that come to the flower divided by all the butterflies in the population. That's why this is so low. Because, yeah, so 22 come to the flower on any given day, but there are millions of them out there that didn't come to the flower. So, yes, it has a fixed rate of success, but that fixed rate of success is extremely low. Okay, that's the difference. All right, so what do we do with this type of data? Okay. All right, so let's see here. Oh yeah, here we have our, the parameters we're working with. So what we want to know is, given that, 22 come to the flower on an average day, how unusual would a count of 15 be? So what we can think of is, we can think of the 22, that's our average rate of success, and 15 is like our data or, our observation on a given day. Okay. So Lane explains the Poisson distribution, but he doesn't provide a calculator for you to use. So if you look here, you're not going to find a Poisson calculator. So what we use is a calculator at a website called StatTrek. All right. So notice if you type in StatTrek or StatTrek Poisson, you can just click on it here to find the calculator. All right. Okay. Now, so when working problems in this class, by the way, there are also binomial calculators on this website. You should use the binomial calculator provided by Lane. Okay, just use that. And then we'll use this Poisson calculator provided by StatTrek. So if you were to use the binomial calculator on StatTrek, you may get slightly different answers, and that's going to make it difficult to grade quizzes and things. So just, that it's not that these are incorrect answers, they're actually a little more precise. We're going to, and they have less rounding errors, in other words, we are going to do it that way so that everybody's getting essentially the same answers. Okay, so let's take a look at what we have here. There are two fields you have to fill in to get an answer here. We need our average rate of success, all right? Remember, that's what, in the case of these butterflies, that was 22. That's how many go to the flower on an average, on a daily basis on average. And then we have a random, they call it random variable, but this is our observation. So how likely are we to see 15? That's what goes here. So 15 goes there. And then you hit the calculate button. Now notice there's all these different probabilities here. And so it depends on which one we're interested in. You may remember with the binomial calculator, we could kind of find out how likely it was to get exactly a certain number of counts or more than a certain number of counts. Okay, so here, this one gives us the probability of getting exactly 15. So notice that's, 0.029. All right, that's what you would be reporting if you wanted to know the probability of getting exactly 15. But this is a low number, so if we were interested in, well, how likely is it to get 15 or fewer, then we're going to need this value. See, probabilities, no, wait. Yeah, probabilities of X, meaning scores that are less than or equal to 15, that's about 8%. So even if you're just looking at the lower end of the distribution, it's not, it's unlikely to see 15, but it's not that unlikely. Now, if you wanted to know an extreme, how likely is it to get an extreme value? So in other words, to get 15 or fewer, or I guess this would be 7 above, right? 7, let's see. Yeah, 7 below 22. So we could look at the other end, how likely are we to get, I guess, 28 or more? Let's see, 29 or more, right? Okay, so add 7 to that. Okay, that would be like a cumulative probability on the other end, so that's like about 9%. Notice this is a little different from what we had on the other value. And that's because this, just like binomial distributions, is not a symmetric distribution. Usually one side is a little longer than the other side of the distribution. It's not a normal distribution. Okay, so what happened then? All right, let's see if we have a conclusion on this slide here. Okay, oh no, we have another example. Well, let's go ahead and write a conclusion for this one. All right. Let's see, we have a couple of different things here. No, we do have a conclusion here. So Lane does not, okay, so when you figure out the probability of exactly 15, that's only about 3%. Getting 15 or fewer, about 0.08%. So 15 or fewer butterflies is unlikely, but perhaps not that unlikely. All right, so we could put our usually the probability, if it's lower or if it's greater than 5%, we don't reject any null hypothesis we might have. That's just looking at one end of the distribution. If you wanted to figure out, well, how likely is an extreme score, then we need to add those two. So this is only looking at one end of the distribution. Okay, I don't think we need to go belabor that too much. I want to go look at some other examples of typical Poisson problems. So here's a classic problem that you may see something very similar to this on a quiz sometime. So we have the Davie Fire Department receives about 7 calls per week. Okay. Well, for whatever reason, There were a lot of calls in October. You know, like 35 people called in. There were like 35 fires set around town. So, you know, looking at some data like that, you might think, well, wow, does that, you know, that seems kind of high. Is this because of Halloween, maybe? Maybe everybody was going crazy in October. I don't know. Maybe it's something about the fall. So how likely is this? Okay. Well, first of all, we could figure out sort of what the mean should be. So what we're expecting is we're expecting if there's 7 per week, right? We're expecting 4 weeks in October. We're expecting 28 per month. Okay, that's really what we need to know here. So 28 per month. So how likely is 35 given we're expecting 28? Well, let's take a look at this for a minute. All right. So here we have our average rate of success. Remember, we're expecting 28 per month, but we want to know, well, how likely is 35? Okay. So exactly 35, again, that's not that interesting. We're sort of interested in, well, is this high? Like, is this way more than normal? Well, we look at the cumulative probability. So how likely is it to get 35 or more? That's how we'd find out if this is unusually high. All right. So let's see here. P greater than or equal to 35. And it's about an 11% chance. So, you know, 11% of the time, assuming people are calling at random, we should be expecting 35 or more calls. All right, so like you could think of, well, they're 12 months out of the year, right? So if 11% of them get 35 or more calls, yeah, October could be one of those. You know, there's bound to be a few of those months when we're going to get that. We could find that out, by the way, if we wanted to. So you can copy this little probability here, all right? And let's, I'm going to need a new one for this. Okay, so here's a new spreadsheet. All right, show you guys how to do this. We'll use that other one in a minute here. All right, let's make this big enough so people can see. Okay, so you know that's what we're expecting to see. So every year we're expecting there to be like 35 or more calls to the fire department, right? About 11% of the time, because the average rate of success is 28 per month. So what about in an entire year? What would we expect to happen? Well, if we multiply that value, A1 times 12 months, right? That tells us how many months we're going to get 35 or more calls. We're expecting, every year, we're expecting there to be at least 1 month. You see, if you round that off, we're expecting there to be at least 1 month when there's 35 or more calls. The rest of the time should be fewer than that. So if you start seeing a lot of months with 35 or more calls, then something's going on. All right, but that's sort of what's expected. Okay, so let's go back over here, see what else we can do with this. All right, so if you look at one end of the distribution, right, just looking at the upper end, we're expecting there to be 35 or more calls about 11% of the time. What about at the other end, like getting low, really low scores? So remember, the average rate of success is 28. That's 7 points above that. So what about 21 or fewer? What would that be? 21 or fewer. So this would be an extreme from the other end. Okay. So let's see. We would want 21 or fewer. That's pretty close to 11%. So it's almost 22% of the time you're going to get an extreme value, assuming that everything is still random. Okay. So I think I have some statements here to that effect. Let's see, this one we need to close. Okay. There we go. All right. So let's sum some things up here. All right. So probability of 35 or more. All right. That's what we found. It's about 11%. what about getting a really extreme score? So assuming that everything's normal, like, the calls are still coming in like we expect them to, we could still get 35 calls or even 21, like an extreme score like that. There's like a 21% chance or 22% chance that that's going to happen in a year. So it's really not unusual. What this is telling us is it's not that unusual to get a really high score on a single month. You see what that means? That's how you interpret these cumulative probabilities. So it's not that unusual to get a really high score like that. Again, notice it's very important that you don't look at exactly 35. That's really not very helpful in terms of drawing a conclusion about whether or not something's going on during the month of October. Okay? Now, you can try this out on your own, but, what if this was like 40? How would that affect everything? I suspect we would get a significant value here, meaning a really low probability. And then we'd have to say, yeah, there were like too many calls coming in October. But I haven't worked that out in this particular PowerPoint, so I'll let you try that out on your own and see what happens. If you're unsure how to interpret it or how to proceed, look back at the example on the binomial data and just see what happens. Okay, so let's take a look at something else. Now, usually being biologists, we wind up with some data like this. All right, so ignore the text over here for a minute. Let's see what we've got here. So being biologists, biologists like to do these sort of randomized samples. So let's say we go out and we have like one of these big squares that we just sort of throw out into a field, and then we go in there and we count all the plants inside the field. This is inside the little square. This is the kind of thing ecologists do all the time to sort of describe population structure of plants or to estimate how common a certain species of plant is or something like that. So here's some data we might get. So we go out, we throw these like rectangles like 10 times. Okay, so we have basically 10 plots. And we go in there and there's two species of plants in there. I don't know any kind of plants. You can call these dandelions and maybe these foxgloves or something. I don't know. At any rate, so we go in and we count all of plant species 1. So our first plot, wow, it's got like 20 of plant species 1, but the second plot only has 2 of them. So right off the bat, you can see there's a lot of variation in species 1. On the other hand, with species 2, we almost always get the same number in there. So how is an ecologist or another type of biologist to describe these things? Well, there's a couple of things that biologists are frequently interested in. One thing we often ask is, are plants in these plots randomly distributed? Okay, that's kind of random. You see that? Well, they both look a little random, but are they really? Are they evenly spaced? These to me look a little evenly spaced. Or are they aggregated? In other words, you have a few plots where you have large numbers of them and other plots where there aren't so many. Okay, so these are really important population parameters that biologists tend to be interested in. Okay, now we can do this in 2 different ways. We can do this using a descriptive statistic. So we're going to try that first. And then we can also do this in a different way where we generate a graph, kind of like we did in the last chapter. There's even an inferential statistic that can be used for this sort of problem. Okay, so we'll talk briefly about it. Okay, so what do you do with this kind of stuff? Well, you may remember when we were working with the Poisson, we usually needed something called an average rate of success, and that's the case here. So what I've done here is in this Excel spreadsheet, I've pasted that data from that PowerPoint into these 2 columns. All right, so I have species 1 here and species 2, and then I've got sums there, so you can see that a total we had like 65 of species 1, right? But the average rate of success was 6.5, so that's just an average of all those scores. Now it's possible to figure out the variance, okay, so that's just this usual formula for variance, so you just hit equal, var, and then put B2 to B11, you see that? So it just sort of figures out what the variance is. And then here we have species 2. Okay, now what we have down here, this is something called the coefficient of dispersion. All right, so we're going to talk a little bit about what those things are. So here we have a little slide talking about the coefficient of dispersion. One of the things about the Poisson distribution, and Poisson, what it does is it is a model of randomness. So if some data follows a Poisson distribution, it is randomly distributed. Okay, so it's a rare event, but it's occurring at random. There's no rhyme or reason to it. So in a Poisson, when data follows a Poisson distribution, what happens is the mean is equal to the variance. Okay, now let's go back and look at that data and see what it looks like here. So here we have the variances and here we have the means. Okay, now look at this one. See how, the mean 6.5, I mean, that in itself didn't tell us a whole lot. It just tells us that on average, one of these plots has got about 6.5 plants, all right? But look at that variance. That's really, really high. And you can see this. See how some of the plots have lots of these plants and others just have a few? So it's kind of like this particular plant is growing in big clumps. You see how that works? Where you have a whole bunch of them together, and then in other places they're just sort of spread out, I guess. On the other hand, in the other species, they're never in clumps. Instead, they seem to, maybe they're repelling each other. So you can get up to about 7 into one of these squares. Maybe that's because, they are a certain distance apart, and that they sort of just barely fit if there's 7. If you have more than that, they just won't fit. Okay, so that's another possibility. And notice how, since these numbers are all close to each other, the variance is pretty low. Okay, so what we're interested in is a comparison of these two things. So if there's a high variance, right, then they're clumped. If there's a low variance, then they are evenly spread out. So the way people quantify this, and this is just with a descriptive statistic, okay, is we take a ratio of the variance to the mean, and that's what the coefficient of dispersion is. So the coefficient of dispersion is the variance divided by the mean. Now if you get a value much greater, I mean if they're equal, you get 1, right? Okay, well that rarely is going to happen with data. But if you get a value much greater than 1, then you would interpret it as being sort of clumped. The plants are in these big clumps, or we say they're aggregated, right? This frequently happens with parasite data. That's something I study. When we actually have a poster in the hall where I did this kind of stuff with some parasites found in lizards. And they also, they tended to be very aggregated. You had a few lizards that had like lots and lots of parasites, and most of them only had a few. On the other hand, they can be overly dispersed when the ratio or the coefficient of dispersion is less than 1. All right? People describe that as over-dispersed or evenly distributed. That may happen, that happens in plants when you have certain species of plants secrete these chemicals that keep competitors from growing near them. So both of these phenomena are very common in biology, and that's why we're spending time talking about how to analyze this type of data. Okay, now what about showing this graphically? So how would we do that? Okay, well, let's see. So as you can see, these are kind of randomly distributed, or evenly spaced, right? And these are really clumped. How does this compare to what would happen if these plants had random distributions? Okay, so first let me show you what we're trying to accomplish, and then I'll show you how we do it. Okay, so what we have here is a graph showing numbers of plants and the numbers of plots that have a certain number of plants. Okay, and what we have in red here, this is a random distribution of plants among these plots compared to what we actually observe in black. Okay, now that's kind of hard to swallow, but let's see exactly what's going on here. Okay, so as you look at this, you can see we have certain counts of plants, and we're going to focus just on species 2. We have certain counts of species 2 in each plot. Now remember, the average rate of success is 4.7. Okay, so if that's true, aren't we going to expect like most of the plots to contain 4 or 5 of the of these plants? So we're going to expect most of them to have 4 or 5, and you can kind of see that's sort of what's going on there. Most of them do have 4 or 5. So we have 10 of these plots total, right? So that's what we're trying to do here. We're trying to show, like, we have 4 or 5 plants. We're expecting most of them, right, to be in our plots. So most of our plots we're expecting to have 4 or 5 of these. That's what you see here. You see those are the highest bars in this particular graph. And this is a good way to illustrate this type of Poisson data. All right, so let me show you how I generated a graph like that, because you guys are going to be doing something like this for homework. Okay, now the steps are listed in this PowerPoint. So here are the steps. You have it in the other PowerPoint I put on D2L as well. Okay, so let's see what we do. So the first thing you do is you start out with 4 columns of data. So you want numbers of plants, and you want observed numbers of plots. Then we have expected numbers of plots, and we have probabilities over here. So let's first talk about our number of plants data entries we have here. What you do is you go back and you look at the counts for this species. So here are the counts for species 2. So what I'm going to do is I'm going to look at, okay, in all of my plots, how many have 0? Notice none of them have 0. Right? Okay, now in all of my plots, how many of the plots have 1? Okay, so I have 1 plot. So remember, this is observed number of plots. I have 1 plot with a single plant. Okay, out of all of my plots, how many of them have 2? Okay, well, none of them do. Okay, notice the total, we have at least up to 7. There aren't any with 8 or 9. So we need to sort of come up with data for all those things. You see how that goes? So here are the frequencies. Now, what I've got down here at the bottom are sums. All right? So notice when we add all the observed numbers of plots, we have 10. Okay. Now what do we do? What about these probabilities over here? So these things we look up with StatTrek. All right, so let me show you how this works. So here we put our average rate of success. So remember, this species of plant, this is species 2, has an average rate of success of 4.7. Okay, so that means 4.7 of the plots, of the 10 plots, right, are going to have, no, I'm sorry, in a single plot you have a 4.7 chance of these things. Okay, so what we have is like a random variable. Well, how often are we going to get, like in a given plot, how often are we going to get 0? That's what this is. Okay. All right, so we're going to throw out a plot, What we're expecting is expecting 4.7 of these planets to appear there. But we might get 0 just by chance. Okay, so how likely is that? Notice here's the probability, 0.00910. So it's